few days ago, Alan Evans suggested on Blue Marble Science's Discord server that one could use a software-defined radio or an SDR to measure the Doppler shift of the ISS. That got me thinking. I had a cheap SDR in the form of a DVB-T tuner USB dongle, so maybe I could do that. So I started trying. I've checked on heavens above when ISS would be passing over my location and started listening on 145.8 MHz during these times. I had little success though, until today. I'm not sure what were the exact factors that helped. A slightly better SDR which I bought in the meantime for other future projects, a different antenna. Anyway, during one of the passes today, the spectrogram looked like this. That may not look like much, but the signal is clearly visible even though rather weak. We can also see that as time passes, that is, as we move upwards in the spectrogram, the signal moves to the left, which means that its frequency decreases. That's the Doppler shift we're looking for. As it turns out, we can squeeze some more information out of it. Now, GQRX, the program I've been using to listen for the signal, doesn't allow us to do much with the spectrogram. It would be nice to pan or zoom it, but that's not an option in this program. Or at least, if we try, what happens is this. We can't pan or zoom the stuff that is in the past, we can only do it with the stuff that will happen, which is not quite what we want. Fortunately though, what it does enable is recording the signal. So when ISS was about to pass over me, I started recording and I got a 6 GB file out of it, containing about 6 minutes of raw signal. Awesome, but now we're back to the problem of analyzing it. GQRX can play the file, but playing it has the same issues as listening in real time. Fortunately, I know math and I can program, so I whipped up a small tool that will allow me to do more. The program itself doesn't do much. It just calculates the spectrum using FFT, the fast Fourier transform, and then dumps a part of the spectrogram into an image file. But then I know which pixels correspond to which times and which frequencies, and that enables some further analysis. Here's what the output looks like. The part drawn, which was hard-coded for now, is for frequencies between 145.775 and 145.825 MHz, and times between 220 and 330 seconds since the start of the recording. The time when recording started is fortunately saved in its file name. Now the spectrogram is generated at an even rate of 30 spectra per second, and the frequencies are also spaced evenly. That means that one pixel corresponds to 1/30 of a second vertically, and since we have 1364 pixels for 50 kHz horizontally, this means one pixel horizontally is about 36.7 Hz. So let's check how the frequency shifted. Let's choose some arbitrary points in time where the signal is visible clearly. I put guidelines in the places where we can see the signal. This turned out to be at rows 820 and 3158. So let's see where are the innermost parts of the signal. So if we zoom in here, here and here are the innermost parts. So this left one is at pixel 670. You can see it in the bottom left corner. And this one here is at 774. Okay, so let's move to the upper line. So here we have, it's barely visible, but we see a line here and here. So here we have the spectrum at 571, and here it is at 675. Now, this part of the spectrum would be the so-called sidebands, resulting from the modulation of the carrier wave. Sidebands are symmetrical around the carrier wave, so the carrier wave frequency itself would be in the middle, corresponding to pixels 722 in the bottom line and 623 in the line here. Let's see what frequencies and times that corresponds to. The very bottom of the spectrogram was at y equal 3300, and that is 142 rows above the bottom. So at 30 frames per second, that corresponds to 4.7 seconds. Now the recording started at 13:26:40 GMT, so this would correspond to 13:30:24.7 GMT. Now the row number 820 is 2480 pixels above the bottom. So again, at 30 frames per second, this means that we are looking at 302.7 seconds after start. So that corresponds to 13:31:42.7 GMT. We have the times, now the frequencies. So x equals 0 is at 145.775 MHz. The total width, 1364 pixels, corresponds to 50 kHz or 0.05 MHz, so the frequency per pixel it's about 36.6 Hz per pixel. So x equals 722 will correspond to 145.775 MHz plus 722 number of pixels times frequency per pixel, and that comes out to 145.8014666 etc. MHz. So let's save this as f1. The underscore is just the result of the previous calculation. Okay, and let's see for the second frequency at x equals 623. So we have 145.775 plus 623 times frequency per pixel. And that is 145.797.837 etc. MHz. Now the carrier wave is at 145.8 MHz when it is emitted. Based on how the actual frequency differed from the emitted one, we can calculate the speed of the source relative to us. Not the total speed though, only the radial component, that is, the rate of change of the distance between us. The formula for the Doppler shift of electromagnetic waves is this. Fo is the observed frequency, Fe is the emitted frequency, V is the relative velocity of the source and the observer, and C is the speed of light. We can rearrange it to get the following one. When we know both the frequencies, we can now calculate the speed. So let's see. Let's take what we had and define the emitted frequency to be 145.8 MHz. So now let's take the first frequency, take the ratio, now we square it, then we do this, again the underscore stands for the result of the last calculation, and we get minus 3000 meters per second, which is 3 kilometers per second, and the minus sign just means that the distance was shrinking. So now let's do the same with the second frequency. First the ratio, then the squared ratio, and then the last step, and we get 4.4 kilometers per second. That's the distance between me and the source growing at this rate. The ISS is supposed to be moving at slightly below 8 kilometers per second relative to the surface, so these values are not unreasonable. That's because, as I said, this is just the radial component, so if the ISS was moving at an angle to the line of sight, the radial component would be smaller. We can do slightly better and simply check what the radial component was supposed to be. Stellarium has the nice feature that when you select a satellite, it shows you this field called range rate, which is precisely the rate of change of the distance from the observer, so what we are measuring with the Doppler shift. Let's see what it was supposed to be for the ISS at the times I calculated the speeds for. That's the first measurement, and we can see that the range rate predicted by Stellarium was minus 3 kilometers per second. An awesome match actually. And for the second measurement, Stellarium shows 4.5 kilometers per second when we calculated 4.4. Still, I'm counting that as a win. Well then, as you can see, the Doppler shift of the signals from the ISS is detectable and measurable even using cheap equipment. I paid less than $100 for the SDR dongle and antennas, and GQRX is free software. Which means that if you really care, you truly can check it for yourself. That's it for today, thanks for watching and see you in the next one.